So with the photoelectric effect, we just want to talk about some experiments. And these aren't specific experiments. These are just more like kind of, we'll call it a thought experiment realistically. So we just kind of want to look at a couple of experiments. We want to look at manipulated and responding variables, and we want to control a few things. And we want to see the relationship between these variables. So the first experiment, what we're going to do is we're going to manipulate the frequency of the incoming electromagnetic radiation, which means we're also going to change the energy of it, because we know frequency and energy, they are directly proportional. And then what we're looking at is we're looking at the kinetic energy of the photoelectron emitted as the responding variable. So we are going to control the number of photons that are incoming, and we're going to control the number of photons that get emitted. Or sorry, the number of electrons that get emitted. So I'm just going to draw some photoelectric surfaces here. So I'm going to draw kind of like a surface with a well. It has an electron in it. Don't mind my, it kind of looks like a whole rest for music. The hat. So in these, we're going to have an electron that wants to be liberated. So in this first scenario here, I have a photon. It's going to come in, and I'm going to say that this photon, let's say, it has an energy of, I don't know, 2 electron volts. Now for both of these surfaces, we're going to say that the work function is 1 electron volt. And the work function is 1 electron volt. Now, the energy coming in exceeds the work function, so this electron will be liberated. So, if I increase, this energy is 2 electron volts. If 1 electron volt of energy has to go into the work function, what that tells us is the energy that's remaining for the electron once it's liberated, it's 1 volt. Through conservation of energy, my incoming energy has to equal to my work function plus the kinetic energy. 2 is equal to 1 plus 1. Great. Now, suppose I decide to up the energy a little bit. Let's say now the energy is 4 electron volts, and the work function is still 1 electron volt. Well, if I have 4 incoming, and I have to pay 1 for the work function, what that tells me is I'm going to have a kinetic energy of 3 electron volts left over. What are we trying to get from this? What we're just trying to show in this relationship is as we increase the energy of the incoming radiation, we're also going to increase the kinetic energy of the electron. So as the incoming radiation, or since we know that frequency is directly proportional to energy, what we know is that if the frequency goes up for the electromagnetic radiation, the kinetic energy also goes up. Or instead of frequency up, we could say wavelength goes down. Conversely, if the frequency goes down, the kinetic energy is going to go down as well. Or we could say wavelength is going up. But keep in mind, frequency going down, it'll go down to a point. Once it goes down below the threshold frequency, we don't have to worry about photo emission. Now the second one, this is where we talked about one of those peculiarities earlier about brightness not affecting photons, or at least the kinetic energy of an individual photon. So this time we are going to change the intensity, or vary that. So this is the number of incoming photons. So by brightness we mean the number of incoming photons. What we would like to see is the responding variable is the total kinetic energy of the electrons that are emitted, and we're going to control the energy of the incident electromagnetic radiation. So this time I'm still going to draw 2 photoelectric surfaces. Again, probably should have drawn this. I'm going to just draw this a little wider. We're going to ignore that little bump there. And same thing again here. So something looks a bit like this. So in each of these, I'm going to have 3 electrons, let's say. So 3 electrons. And we'll say the work function of each of these surfaces is 1 electron volt. Now, here's the deal. Let's say I have 1 photon coming in, and let's say it has an energy of, I don't know, 3 electron volts. What we know, and this is a very massive oversimplification of the photoelectric effect. It's not actually this simple. If you do work at the university level, you will expand on this in way more detail, but we are oversimplifying it. What we are going to do, the rule we're going to have is 1 photon liberates 1 electron. So if I have 1 photon coming in, it will only liberate 1 electron, and that electron is going to have kinetic energy of 2 electron volts. So it's going to be the difference between this incoming energy and the work function. So 1 photon equals 1 electron liberated. So it's kind of a one-for-one exchange. Now, we're going to vary the brightness. So this time, instead of having 1 photon come in, this time we're going to have 3 photons come in. All 3 of these photons are going to have energy of 3 electron volts. Now, what the classical perspective would say is if we had 3 of those photons coming in, they have a total energy of 9 electron volts. They are going to liberate 1 electron. After paying the work function, we're going to have 1 electron emitted with 8 electron volts of energy. That would be a great way to think about it based on classical physics. That's not what was observed. We have to talk about 1 photon in, 1 electron out. If I have 3 photons coming in, we are going to liberate 3 electrons. And each of these electrons emitted, they are going to have a total kinetic energy. They are going to have a kinetic energy of 2 electron volts each. So this is a really important point. If we change the number of photons, if we change the brightness, the kinetic energy on the individual electron does not change. In this case, it's 2 electron volts. This case, it's 2 electron volts, keeping the frequency constant. Like, we haven't changed the value of the energy. But the total kinetic energy overall has changed because now I have 3 photons with, 6 electron volts of energy in total. But the key important point is brightness doesn't affect the kinetic energy on an individual electron. So in this case, 3 photons, we're going to have 3 electrons liberated. So again, we're thinking of it kind of as a one-for-one. But let me re-emphasize, that is an oversimplification of the photoelectric effect. All right, just the last thing I want to talk about. When we talk about electrons moving, we know that for us in physics, the definition of we use movement of electrons to define current. So a lot of times you will see this term of photocurrent, which has to deal with how we're measuring those number of photoelectrons emitted per unit time. So we know from our definition of current, it's just the charge divided by time. Or we can have the number of charge carriers, for example, the number of electrons times the elementary charge divided by the time. So there's some things that we can infer from this. If we increase the intensity, we're going to increase the number of photons emitted per unit time. So increasing the intensity will increase the photocurrent. And then conversely, if we decrease that intensity and decrease the number of photons coming in, that's going to decrease the number of electrons liberated. So that photocurrent will decrease. And then if that frequency does go below the threshold frequency, we will have no photo emission of electrons. So there will be no current registered in that case. And then we also know from Science 9, I believe, we know that current and potential have an inverse relationship. So as we increase the stopping potential, we decrease the current. Vice versa. That comes from the statement of Ohm's law and some other things. But yeah, just know about that. And the last thing, and this is going to tie into stuff we're going to look at a little bit later. When we brought the wave model in and started studying the wave model, it certainly cast some doubts on the particle model because we had some really, really solid evidence for the wave model that certainly made the particle model kind of put it on shaky grounds. But the whole concept of the photoelectric effect, it reintroduces the particle model, and it essentially tells us we cannot ignore the particle aspect of light. And the reason for that has to deal with the fact that, it comes around that whole idea that the intensity of the beam has no effect on the energy actually being emitted. Because we talked about, we could have the most intense beam, but if it's not the right frequency, it won't emit any electrons. Whereas we could have a very faint beam, but if it doesn't hit that right frequency, we could have the faintest beam, but as long as it's above the threshold frequency, we are going to emit that photoelectron. Now, what Einstein had said is this all comes from the fact of quantization. Instead of thinking of all of that electromagnetic radiation just hitting the surface, it comes in bundles, it comes in packets, it comes as quanta of energy. So in order to explain the photoelectric effect, Einstein treated the energy incoming of those photons as well discrete particles. So he's treating energy as a particle to explain the photoelectric effect. And then that particle or that photon coming in will emit that electron. So the photoelectric effect demonstrates the idea that the particle model of light has validity. So even though we've saw work by Huygens and Young showing that light behaves as a wave, the photoelectric effect also reintroduces that we have to treat light as a particle as well. We cannot just dismiss that idea. And we'll talk a bit more of that when we look at the Compton effect.